In this chapter, we're going to discuss hashing. Hashing is a very broad concept. It can be used for identifying objects in a unique manner. Since you can do this, you can also use it for searching items in a huge set. Or it can be used for encoding. So it uses both in telecommunications and also in, for example, zip or RAR files. So in compression, in other words, or in many different fields. In this chapter, our focus will be mainly identifying objects in a unique or close to unique manner, and therefore being able to search items in a very efficiently. So the basic idea is you have some key that identifies a record. For example, as we discussed earlier, either the name of a student or the student ID, social security ID, whatever. So there are the keys and there are the indices. And the hashing function defines a mapping from these keys to the corresponding indices. It provides an efficient way of searching in this manner if this index belongs to the item in the array. Each element is found with a single hashing operation, so that's why it's so efficient. So let's consider two different scenarios. In scenario one, we are trying to store the records about about 1,000 students, but we're using the incremental IDs of the students. That means the IDs of the students are starting from 0 all the way to 999. So simply we can use an array with 1,000 elements where the student ID is also the index in the array. Now, consider another scenario where again we have these 1,000 students, but this time we don't have their IDs increasing in an incremental manner starting from 0 to 999, but we're using, say, their social security IDs, which are typically, for example, 11-digit numbers. So you have up to 99 billion different values for these social security IDs. So if you try to construct an array based on the social security ID, where the social security ID is the index of that student, then you will have an array with billions of elements, and you will be using only thousands of those elements. That's a great waste of space, and also in many cases you cannot even create an array of that size, so it will be also most of the time an infeasible solution. So our approach is actually directly referencing the records in a table, but to find the keys, we will be applying what we call a hashing function, which is actually a formula. It's a sequence of arithmetic operations that you're performing on the key to find the correct index. And that index then will be used to map to the table addresses. So hash function is the mathematical function that translates the search key to the index in that table. So what we should be looking at would be then the hash functions and their corresponding hash tables. There are different ways of doing hashing. Actually, the topic of hashing and writing hash functions, writing good hash functions, is a topic on its own, which typically takes one semester of lecturing. So, of course, in this chapter, we will be very brief. We will be looking at the most basic, simple ideas. So the first one, the most basic one, would be what we call the direct address tables. The assumption is there is a direct one-to-one correspondence between the keys and the corresponding index. So the index varying from 0 to m-1 if you have m elements. Then we can create an array if m is not very large. And as we discussed earlier, the keys would be directly mapping to the index. So each position or the slot in the array would would contain a pointer to the record about that student, for example. If there is no such student, then that pointer should be null. What's the cost? The cost would be the size of the array, and also finding the key, which is easy. So the size of the array depends on the largest possible value. If m is not very large, then it is feasible. But if there are only few keys, but a wide range for the index, then you would end up with an array which is sparse, which means most of the elements of the array are not used. They're either null or zero, depending on what type of data structure you have defined. So we would like to write good hash functions that will transform these keys within a predetermined interval. So we have a limit on the lower and the upper bounds of the possible index values in the array, which stores the record. So let's first look at the scenario where the keys are actually numeric values, numbers. So if we're talking about a hashing table of size m, we take the key. Since it's a number, we can apply a mathematical function on that and end up with a value. The most frequently used operation there is the modulo operator. So if you have an array of size m, which is index ranging from 0 to m minus 1, then you should be using modulo m, which will always give a value between 0 and m minus 1, which is a valid index into the array. However, if the key is a string, then you cannot apply modulo operation on a string. So what you can do is you can treat the binary representation of the key, which is a string, as a number, and then apply the hash function. Now, how do you treat a string as a number? What you can do is you can take the string and process it character by character and represent each character by its corresponding, for example, ASCII code or whatever code that's being used. So if each character is represented using m bits, for the case of ASCII that would be 8, but you don't have to use ASCII, then the string can be represented as a base m number, because each character position in the string would correspond to a value in base m. Here's an example. Let's consider a string which is a key, so A-K-E-Y. Now we have their codes. As I said, you could use their ASCII codes, but here, rather than the ASCII codes, we'll take it simple. We're talking about the English alphabet, so there are 26 different characters. That means I need 5 bits. 4 bits would not be sufficient, so I need 5 bits. As we discussed earlier, with 5 bits you can represent 32 possible values, not 26, which means 6 possible values will not be used. But anyways, we're not going to use it. 5 bits is the minimum that we can use. So this string a key is now composed of the characters A, K, E, Y. Therefore, it's composed of the values 0001, 01001 goes this way, where these values, these codes, are actually their order in the alphabet. So A is the first character, therefore it's 1. K is the 11th one, therefore it's 11 written in binary. So this is the binary notation for 11. Y is 25th one, so this is the binary notation for 25, whatever. So the values we have are 1 for A, 11 for K, 5 for E, and 25 for Y. But I should be able to differentiate between the string a key or, for example, Kia, where A is not the leftmost character, but it's the rightmost character. Now, these are two separate strings. Therefore, the hash functions should give different values for these. They should not be the same. Therefore, just as we do with regular numbers, remember, for example, a value like, say, 57 is equal to what? 5 times 10 plus 7 times 1. Or a value like 6,952 would be 6 times 1000 plus 9 times 100 plus 5 times 10 plus 2 times 1, where this is actually 10 to the 0, this is 10 to the 1, 10, this is, of course, we don't write it that way. This is now 10 to the 2, and this is 10 to the 3. Okay? So, if we translate the string eki in this way, but this time we don't have base 10, because in the case of numbers, we're using the Arabic numerals, so we're using base 10. Therefore, our base is 10, but this time we're using 5 bits, so our base is 32 rather than 10. Therefore, rather than saying 10 to the 0, we say 32 to the 0, 32 to the 1, 32 to the 2, and 32 to the 3, multiplied by the code of the corresponding character. Therefore, if my string was not a key, but it was kia, in that case, I would be using 11 times, this time 32 to the 3, because this is bit 0, or character 0, character 1, 2, and 3. These are the positions. So E is 5 times, 32 to the 2, plus Y is 25 times 32 to the 1, plus A is 1 times 32 to the 0. So it would be a different number. Although the letters are the same, since the orders are different, they're different words, therefore the values would be different. Anyways, for the case of a key, this would be the corresponding code for this key. So I am able to translate this string using a hash function named f, which gives me the value 44,271. This would be my mathematical function, or my hash function. However, if the keys are very long, then I could easily have an overflow. The number would be too large. So the solution to that problem would be what we call the Horner's method when we try to compute the hash function. So the Horner's method works as follows. Now, note that the mathematical function we defined was actually a polynomial of degree n, whatever n is. So we have some factors like a sub n minus 1, a sub n minus 2, which were actually the codes we had here. Like for a, it was 1, for k, it was 11, whatever. So these are the a sub n factors here. And x is my base. In that example, x was 32. N would be the character position. Remember, the rightmost one is position 0, and it gets incremented by 1 as you go towards left. So it would be this formula, polynomial definition, you have in the first line. But we could easily rewrite it as follows. Now, you can take this into x parentheses. If you take the first two terms, you can take it into x parentheses. So it would be like this if you take it to the x parentheses. And multiply by x, x, x. So in total, if you have n minus 1 x's here and another one here, so in total it will be n x's multiplied. So you would have an times x to the n. An minus 1 would have 1x less, so it would be x to the n minus 1. An minus 2 would have 2x's less, so it would be x to the n minus 2, so you will end up with the same thing. Okay, so we are just taking into x parentheses. So for example, if you had an expression like this, we could take it to the x parentheses as follows. Now, how does it help me? If I have a very long key, like the string here, let's say our string itself is the string very long key, and here we have the corresponding codes for these letters, and these are the binary representations, and here we have the base 10 representations. The value of this very long key would be calculated in this way, which would be a huge number, and typically you would have an overflow. However, I can apply the following trick. Since I know I will be working with mod m, where whatever m is, m could be anything you wish. So you can take this number, okay, and work it as follows. Starting from the leftmost character, that its code times our base, which is 32 in this example, plus the code of the next one, e, which was 5. So take this. You don't need to calculate 32 to the n. Take this and do modulo m. That would be h0 in Horner's method. H stands for Horner's. So h1 would be the result of this times 32 plus 18 modulo m. So you repeat this for all h values. The last one would be the overall value. Now note that in every stage, since we are taking the modulo m here, the result would be between 0 and m minus 1. In other words, for all h sub I, it's guaranteed that it's not m or larger. We know it's a value between 0 and m minus 1 inclusive. This way we have contained the individual terms to be less than m. Therefore, at any point during this calculation here, we will never end up with a value that overflows our integer or long integer, whatever. So we will not have such problems. So this method, Horner's method, would allow us to process strings of any size. It could be thousands of letters long strings, still it would work. So the code that implements this is given here. This is for the case of 32, base 32. That's why we have named this as hash 32. Simply, you take a parameter with the name or string, whatever it is. You take its length, which will be your key length, and initializing h to 0, one by one, for each letter in the string name, you take that plus 32 times the previous h value. So initially it was h0. 32 times the previous value plus the current character's code, whatever it is, modulo m, where m is our table size, because our table is from 0 to m minus 1, remember. That would be the new h value. So from h0, we will be calculating h1. From h1, we will be calculating h2. And we will keep repeating this for all characters in this key. And whatever the final value is, that will be the hash code of the overall string, no matter how long that string is. Here, the index is an integer based on the hash function, so it's between 0 and m minus 1. Initially, everything in the array is empty, so we have blank slots. Now, I should be able to represent a blank value and a legitimate value. So it is best if you have a sentinel value, like say if the possible values are all non-negative, then you can use, for example, -1 as a sentinel value to mark that that slot has not been touched at all. There is no value placed in that slot. Or you can use null depending on what type of an array you have. Insert will apply the hash function, which will give us an index, and we will go to that slot in the array, and to that slot we will insert that value. And search will be searching for a key in the table. So again, it will apply the same hash function, which will give us an index. We'll go to that index in the table and see if it's the sentinel value. If it's the sentinel value, that means that value does not exist in our hash table. If it's not sentinel, then it's the value that we're searching for, and we will return that value. How about the size of the table? It should be some size which is typically different from the number of records. Definitely M should be, in this direct table case, it should be larger than N. Otherwise, you will not be able to fit all elements into an array which is smaller than the set of elements. So the load factor, which is defined as the number of elements we have in the set over the size of the hash table, is represented by lambda, and it will be typically a value less than 1. We would like to keep this lambda factor, the load factor, lambda, not very low. So a rule of thumb which works well is around 60, 70, or 75%. If it goes beyond that, note that, for example, if it's 75%, it means there's 25% still available space, but it also shows me that my hash table is about to get full. So I should take some precautions so that I don't fall into the case that I need to insert an element and my hash table is full. What kind of solutions we can find? We will discuss that later in rehashing. We prefer a prime value for the case of M. This provides us an even distribution of the keys. That means we do not want to take, for example, modulo 10, modulo 20, or modulo 24. But we would like to have prime values because as divisors, prime values are better. They provide even distribution of the keys. Otherwise, you could easily end up keys mapping to the same slot in the array.